Hi, this is Merlin. I'm just gonna talk about Valorant today. Yesterday I just talked about the how do you really make some kind of beat tree, and today I'm just gonna talk about my code over here. But I'm trying to working on it right now, but so it's not really accurate because I'm trying to refactor a whole of things. So here, let's see. Um, the basically the beat tree is I just talk about beat tree is it's beat tree is just kind of like trying to solve the problems that of like normal binary tree, because normal binary tree it can have like less children. So if there's a depth of the tree is gonna be increased, the more the time complexity will increase. So we just kind of trying to handle this kind of issue, and B tree is kind of a very practical data structure that is being used in nowadays. Like for example, the database indexing. So I'm just gonna try to like I already implement like bunch of this code here. So the page. So in the database, the page just is just like when you're trying to think about the node of the B tree. In the database, the page is like kind of node of thing. It can have the multiple record keys and children. So the search. So if you look at the search part, if you look at this code here, so we're just gonna traverse encounters the query key. So the search key. So based on that example, you increment the increment index, um, till you encounter query key. But if you didn't encounter query key, and if the query key is smaller than search key, and you make break, and you traverse one more to find the child, uh, uh, to search it for the child index. So this is kind of like the code for the searching for the child index. So search query is really easy. It's just like recursive traversing. But I think the insertion is kind of hard. So I wrote some kind of description here. So if there's more children, we have to traverse till we encounter no children. I can leave. So example, if there's more children, we have to traverse it. I mean like it's of course because the binary tree and the B tree is really kind of same. You traverse until you encounter the last node and you have to insert it. You don't insert the root of the tree. So we have to traverse until we counter the no children, also called as a leaf. Since we are in the B tree, there's no explicit left or right variable. So we have to compare to get the child index. For example, you have the node that have one key, the 20 keys value, and the left child is gonna be 10, 15, and the right is gonna be 12, 23. So that's gonna be the middle of here. So you want to index the new key 30, so you have to compare the index of current key. The 30 is bigger than 20, so it doesn't belong to any key, any index. So it exiting the current key. So we're just gonna go to the right index here. We're gonna go in here, but the index of this part is children that one, right? But how do we really get this one index? We just have to can get the one index by comparing this key. So which is gonna be the 30 is bigger than the 20, so it's gonna be 20. The value of 20, the index of 20 is equal to the node that keys that 0. Since the 30 is exceeding 20, so we just plus 1 of here. So basically we are able to get the children, the keys of the target children of here. So which is 1. So that means that we have to traverse if this is leaf, which also means that there's no children. If there's more children, we traverse, we get a traverse the direction of here. So if the record keys, so if the target, example, our target is 30, and if the last index of the record key is even smaller than target, we just have to go to traverse it. But if the target overflow is false, oh sorry, no, it's not. It's not how you do it. So basically the problem is that what if you already encountered target key? Just, wait, hold on. Let's say you have 10 and 20 and 30. Let's say 20 here. So if you want to go, let's say you have a 15. 15 is gonna be the 15. The index is gonna be smaller than 20. So we go left here. When we go left here, oh yeah, it's right. It's right. So actually, the purpose of this code is just getting the state of here. So if you go right node, you just have to traverse the exiting the index of here. If it's not, we just have to find the element that has the small gap between the target query key. So if it's like 15 here, so but we already have 10, so 15 is between 10 and 20, so we go plus 1 of the 10 index, so which is gonna be the 0 plus 1. So it's gonna be so we just traverse one more. And if the page is full, if the parent node isn't null, we just have to insert the new page to the parent. So that's a really kind of hard thing, but as you'll see, my code isn't really it doesn't implement it really well. If you look at here, yes, but you don't really make it like this. This is actually correct, but there's also duplicated, and I think there's something wrong with this code. Yeah, I think so. There's something wrong with my code. I think the problem is that then giving the limitation of the code, limitation of the node. I think it doesn't really good. I think the main problem is like kind of this part. Yeah, I think there's something wrong with insert with the paste node. But never mind. So I'm just gonna try to implement it. So this is how you really imagine. But also the implement B tree is really kind of hard using JavaScript because there's no fully good code there. There's no kind of the separate of. It's not really object oriented. If you look at other code in the Geek News or whatever, so it's not really object oriented. It's not really readable code. It's just the kind of code that ChatGPT made. So I'm just trying to implement myself. I didn't really use the ChatGPT for it. I'm just use ChatGPT for like really minimal base, like 10% of it, but 90% I just made it via reading some kind of research papers here. So this is it. Have a nice day. See you next time. Bye bye.